Okay, let's start. Okay, so today we're going to continue talking about trees, and I think I'm going to finish trees today. Let's see what kind of topic we're going to discuss next. But first, trees. Okay, still trees. I still want to give you a very brief summary about what tree, the basic tree and the random forest we discussed last time. A tree method is growing. Right? Okay. Now, corresponding to x1, x2, if x is 2-dimensional, then the tree is corresponding to make recursive cuts. Okay, so one cut here, the other cut, maybe another cut, right? So every time we cut a different region, make recursive cuts, so that we end up with a tree kind of structure, right? Now, the algorithm that we discussed, so because there are different algorithms to grow the tree. And one thing we should always know is when we grow this tree, the more cuts I make, right, the more complicated my model becomes. So the model can become increasingly more and more complicated, right? Okay. What is the optimal amount of tree we should grow, or optimal amount of cuts I should make? Is essentially the bias variance trade-off that we always talk about, right? There's underlying U-curve. We want to find the optimal point. The algorithm that we have discussed so far is a two-stage process. In the first stage, I grow a very large tree. I just grow a very large tree, just make cuts until some stopping criteria, like, for example, until there are only, for example, 10 data points left, okay, in each leaf. So we grow a very large tree, and then we prune it back. The way to do it is I grow a very large tree on the training data, and then I can test, okay, I can take the tree, I can go to some test data, okay, some validation data set, and I can estimate the error, at each point, each node and each leaf on the validation data. And I can say, okay, can I delete this, okay? Can I delete these two leaves? Maybe after I delete it, the error here is smaller than the combined error here. In that case, I would delete the leaf. Okay, delete leaf. That's called pruning. So pruning is to grow a large tree and then cut it back. And the way to do it is to we fit on the training data and then we take it to the validation. On the validation data, I can calculate the error at each point. And now I know, okay, look, this doesn't make sense because the error here is smaller than the combined error here. So let me delete it. Let me delete this one. Maybe this one also doesn't make sense. Okay, so let me cut it all the way to here. So in the end, we do this. We find out the optimal tree structure by pruning back. So grow a large tree and then prune back. That's the algorithm we have discussed. Right? There are other algorithms for growing the tree, but this is a very popular one to do it. All right. The other thing I want to talk about, the random forest idea or the bagging idea. We first go from tree to bagging. Now, the benefit of a tree is that it gives you a nonlinear relationship, right? And automatically models the interaction among the different variables. But the drawback is it can be highly unstable. It could have low bias, but high variance. So anytime if you have a method that is relatively high variance, you can bring the variance down by doing the bootstrap aggregation, which is called bagging. And by bootstrap aggregation, I mean we generate many bootstrap samples from the original training data, and we fit a tree on each bootstrap sample and simply average them, right? And by averaging them, we lower down the variance. So that's called bagging or bootstrap aggregation, right? Okay. Now, the bagging turned out to be, if you have a large number of x variables, and all these x variables are highly correlated with each other, then even bagging, I shouldn't say the x variable is highly correlated. The bootstrap samples are highly correlated with each other, right? So in the end, when you fit the trees are highly correlated with each other. So to further decrease the correlation among the tree, in order to really bring the variance down, we can try to make each tree more independent. How do we do that? Well, every time when we cut, we only consider part of the variables, a subset of variables, not all the variables. In this case, if we have x1, x2, if we only have two variables, that means every time I cut, I only consider, for example, the x2 dimension, okay? So I only consider cutting along this dimension. I don't consider cutting along x1. So that's on one bootstrap sample. On the other bootstrap sample, I may only consider cutting along x1 and never do not consider cutting along x2 at specific splits. Now, in that case, the two trees will be very different from each other, okay, more different from each other. They become more independent, so that when we average them, the variance is really brought down. Of course, there's a cost, right? The cost is if we do not consider all the variables in every cut, then our cut is not going to be optimal at each split, which means that our individual tree will have a higher bias. So it's again a bias variance trade-off. I increase the bias of each tree by only consider a subset of variables when I make each cut. But then when I can bring the total variance down, okay, to achieve a better result in the end. And that brings us the random forest, okay? Random forest idea. So random forest is really baggy, but every time when I do a split, I only consider a randomly selected subset of the variables, not all variables, when I consider them for splitting, okay? All right. One thing I want to mention now, but we will talk more when we discuss causal inference. There we go. So we are still talking only about prediction right now, okay? How do we make the best model, right? Predict the data, forecast the Y. We're not talking about causal inference. We will discuss causal inference very soon, right? After this lecture, we start to talk about causal inference. But in causal inference, let's imagine a very simple task. Suppose I want to know the impact of a policy. Okay? I want to know the impact of policy on economy, okay? Maybe on GDP. Right. Now, a typical way to do that, suppose a policy, I don't know, high-speed rail or some other government program, right? So in program, right, so I can do this policy, not do this policy. Now, I can put GDP here. Right, so if I collect the data on the implementation of policy and then the GDP, right, I can put the GDP on the left-hand side, I can put the policy on the right-hand side. But then oftentimes the effect of the policy depends on some other variables. If I have this, maybe the policy is minimum wage or something, right? So it depends on the local condition. So it depends on, for example, the population, right, size. It depends on the population size. It depends on maybe local income, right? It depends on gender composition or something, right? So typically it depends on a lot of other variables called Z. So what you really want to, so the model, suppose the model you have is GDP as a function, right, of your policy and other variables you want to control. And these other variables include, population, size, income, etc., gender, right, whatever, right? A bunch of other variables. If we only do a linear regression, then that's just beta 0 plus beta 1x plus beta 2z. The causal effect we're talking about here, the effect of the policy on GDP growth is the beta 1, right? So beta 1 is the effect of policy. Recall that this beta 1 is a constant. Maybe the beta 1 is 0.2 or something. Does it vary with z? No. Does the beta change depending on z? No. Regardless of z, the beta has the same, in other words, the policy has the same impact on GDP, regardless of the z, right? So, okay. Now, how do you make the policy effect dependent on z? Because typically, the effect of policy on the GDP should vary according to where you are, right? According to which city you are, according to the population size, right? So it should change with z. Now, of course, you can always do interactions, right? You can always have x z1 plus beta 3 x z2. You can always do interactions. But these interactions, if you have a large number of z, how many interactions should you do? How to do the interactions? Is there any way to automatically do the interactions? Using a tree, right? So we just said that tree is a way to automatically detect nonlinear relationships and automatically do interactions, all right? So in other words, if we're talking about heterogeneous effect, right? Heterogeneous. So in causal inference, there's a word called heterogeneous causal effect, okay, or treatment effect. Heterogeneous causal effect, meaning that the causal effect, which is the policy effect on GDP, changes depending on other variables, right? Changes depending on the value of z. So to do that, a very natural way is to do a tree, right? So if let's say we have population size here and income here. Suppose this is Z1 and this is Z2, and I have a policy, and I want to know the policy's impact on the GDP, then I can do a tree that cuts in the Z space, all right? And make a cut here, cut, a cut, a cut. So what does it mean? It means that if Z is here, if I'm here, if I'm in this income and the population range, I have this kind of beta effect on GDP. If I'm here, then I have another beta effect on GDP, right? So the effect of beta, the effect of policy on GDP varies depending on which area I'm in. In other words, depending on the value of Z, okay? So it's automatically it's automatically generating the so-called heterogeneous causal effect. The effect of causal effect, sorry, the effect of this policy will vary depending on which space in the G space, right? Where in the G space we are. So it depends on the value of Z. That's called heterogeneous causal effect, right? So this is the idea behind a lot of tree application nowadays in very recent, right? Because all this is recent literature. So this depends on the recently when people are doing heterogeneous causal effect. So many people are starting to use random forests or starting to use trees for that purpose because it's just an automatic way to do it. Okay, another insight I want to talk about at the beginning today is how do we understand the tree model? Now the tree model is tree, okay? The question is it parametric? What is it? Is it a parametric model? Or is it non-parametric model? Which one? Is it parametric? Is it non-parametric? Now what is a parametric model? A parametric is a model that has a formula, right? Has a parametric form, there's a beta you can estimate. What is a non-parametric? A non-parametric is basically, like I said before, all non-parametric methods are different versions of local averaging, right? So if I have a bunch of y data, okay? So non-parametric model, if this is x, this is a y, I want to use x to predict y. I don't have any model. Every time, if I want to predict y in this space, like at this point, if I want to predict y this x, all I do is just averaging these data points in the neighborhood by giving them different weights, okay? So the easiest way, the most simplest way to average them is to simply give them all the equal weights and average them. That's the KNN. Right? In every neighborhood, I take n values, I take n points around the x point and then just average them, right? The KN method, that's a typical non-parametric method. I don't have any model, just averaging the data in the neighborhood to give me a prediction y here, okay? That's non-parametric. So, a non-parametric model is a tree of parametric model. Now remember, the benefit of non-parametric is that there's no model, right? So if there's no model, we're ultimately flexible. We're very flexible, okay? So we don't constrain the model to be any particular shape. It's non-parametric methods are capable of modeling very complicated functional form because there's no functional form assumed. I can get any shape I want. The drawback of non-parametric is just requires a huge number of data for the fixed dimension, right? And once the dimension go high, you typically don't have enough data for that. So when in high dimension, non-parametric methods don't work because we just have too few data. In order for non-parametric methods to work, we need a lot of data points in every neighborhood in order to generate prediction y. In order for parametric method to work, like linear regression, how many points do we need for linear regression? So suppose there's only one dimension, x. How many points do I need? I need 2 points, right? 2 points, linear regression, I'm done. Okay, so the parametric methods is a way of saving. So there are two ways to think about. One way is parametric methods save you the data, right? Save you. You don't have to have a huge amount of data to estimate parametric model. The other way to think about parametric methods is that model. What is a model? Because non-parametric has no model. But what is a model? There is a famous saying that model equal data reduction. Okay. So modeling is a data reduction technique. That if you want to remember when we talk about KNN, we said if we want to do k nearest neighbors, every time we need to store the entire data data set in our memory, okay? Or, right? So because every time I want to make a prediction, I have to calculate the distance to each point and figure out what are the neighbors, and then average the neighbors to give me a prediction. So I need to store the entire data because there's no model. And once you have a model, for example, linear line, that you are saying, okay, I don't really care about the data because the pattern in the data can be summarized by the linear line. So I only need to memorize the linear line, which is beta 0 plus beta 1. Just two right? Beta 0, beta 1. That's it, right? For in one dimension case. So the model essentially is data reduction, right? It reduces the data. Now, if we have a model for the world, like quantum mechanics, okay, again, a physics theory for how the world operates, then essentially say the world is infinitely complex. So much data, every data describes the world, but we are going to reduce it to a simple model that describes how it works. Right? So model as data reduction. Now, a parametric model is a model, right, that reduces the data into a simple parametric form. That's why it's parametric, okay? All right, so non-parametric model do not really reduce the data. You can think about that way. Parametric model reduces the data into a simple parametric form you can memorize, and you don't have to keep all the data. All right, so tree, again, question. Is tree a non-parametric? Is a tree a parametric model? First of all, is tree parametric? Do tree have beta that we learn? Do you have beta that we estimate? Remember what I said at the beginning. Fundamentally, what is the tree? We have another name for the model. Piecewise constant. All right? So, and the piecewise constant is a parametric or non-parametric? Piecewise constant is y equal to beta 1 if x belongs to region 1 plus beta 2 if x belongs to region 2. That's piecewise constant, right? So it's parametric or non-parametric? Parametric, of course. Okay. It's similar as fitting just constant model, but I'm just breaking into different regions, constant here, constant here, constant here. That's a parametric model. There is a beta that I learned. It's beta 1, beta 2. If I divide my data into 1, 2, 3 region, then how many beta do I have? I have 3 beta. So I basically estimate 3 beta values. So I have reduced my data into 3 parameters. 3 parameters summarize the data, right? That's a data reduction. We have a parametric model. Okay. Well, maybe you are thinking this, okay? Maybe you are already getting there. But a tree is also non-parametric. So I can say a tree is parametric, or I can say it's non-parametric, because a tree is a piecewise constant model. But I can also say a tree is just like a k nearest neighbor model. Why? Again, let's give a number of data points. Okay, so this is y, this is x. If I do piecewise constant, I divide into 1, 2, 3, 3 regions, and okay, here's a fit, here's a fit, here's a fit. That's a parametric model, right? Three parameters, beta 1, beta 2, beta 3. But what if I continue cutting? Well, I say, okay, these two, let me cut it here. These data points, let me cut it here. Right? Cut it, cut it, cut it, cut it. If I continue cutting, in the end, what do I have? I have for every point, what is the prediction of y? Y is the prediction of averaging the point around it in a very small window, correct? And for this point, it's averaging the point around it in a very small window, very small window, very small window. And what is that? Isn't that the k nearest neighbor? Because for k nearest neighbor, for every point, I'm generating prediction using the data points in a very small window around it, right? And the k nearest neighbor, and this tree is essentially doing that, correct? The only difference is what? The only difference is better than k. Why? Because the window is generated from data. So it's not a fixed window. Okay? So, right? So in other words, that's what we call adaptive window. Okay? You can think about the tree as adaptive nearest neighbor. Now, k nearest neighbor is with a fixed number of nearest neighbor, right? K nearest n equal to 5. What does it? K n equal to 5. Okay. What does it mean? It means if I have my data that look like this, 1, 2, 3, 4, 5, maybe like something like that, right? So for the k nearest neighbor method, if k n equal to 5, for this point, I'm always going to use these 5 data points. Okay, always going to use these 5 data points. The window doesn't become large, the window doesn't become small. But what if these 2 data points are here? That clearly has sort of like a different, so they have a different personality than these guys, right? They hang out together. Okay. So in that case, is it still reasonable to use this window? Perhaps not. The KNN method doesn't care. The K method says if I want to predict the y at this point, I'm averaging these 5 guys. But for the tree has the ability to make a further cut, right? So that this becomes a better fit. Right. So in the tree, the window is adaptively chosen or adaptively generated from data. It's not a fixed. So it's even better to KNN in that regard, right? You can say that. So is a tree a parametric or non-parametric, right? Now the answer is if we are only making, if we have a very, if I have a data set like this, if before looking at the data, if I say, okay, I'm just going to make 2 cuts. Just going to make these 2 cuts. And I'm going to fit the model. That's a parametric piecewise constant model. But then if I say I'm going to continue cutting into a very small window, and then average them, in the end it's a very small window, it's a very complicated tree. It's almost a non-parametric method. Okay? There is still beta that we learn because it's always piecewise constant in the sense that it's always beta times, it's always in each region there's a beta. So you can always express a tree in piecewise constant form. So it's always parametric in that sense. But there's a key difference between a tree and a traditional parametric model. Traditional parametric model, the complexity is fixed. It doesn't grow with data. It doesn't grow with the complexity of data, right? Its complexity is fixed. What is traditional non-parametric? A traditional non-parametric like KNN is a method whose complexity can change with the data, right? So if the data grows more complex, KNN fit will become more complex. So the complexity changes depending on the data. That's a traditional non-parametric. So a tree has both. A tree has a parametric form, but the parametric form is able to adaptively change with the complexity of the data. When the data become more complex, it becomes more complex. When the data is simple, it becomes simple. So it is a parametric model that is able to be very, very flexible. So it can become very non-parametric, or it can be very parametric. Okay, depends on what the data looks like. And in fact, that is the characteristic of most machine learning methods. Or let's say, I really don't like the word machine learning, right? Because it has been really misused, or everybody uses it. It's all become meaningless. But let me just say it's the characteristic of most adaptive methods, okay? Which is the characteristic of many machine learning methods, right? But it's the key feature underlying all these methods like trees and also neural networks that we're not going to discuss this term. In essence, these methods are adaptive. Right? They can change from simple parametric form to almost very, very, very non-parametric. In that sense, so whenever the data changes, it has a lot of ability to adapt to the data. That's why they call it adaptive method, and that's why they perform. In many situations, they can perform better than the traditional parametric method, and they can perform better than the traditional non-parametric method. Okay, so that's the underlying principle. All right, so we talked about random forest last time, and today we're going to discuss another kind of way. So random forest is an ensemble method, which essentially brings many trees together, right? And let's form a big family. It's called ensemble. Okay. Now there's another ensemble method, very popular. It's called boosting. So we're going to talk about today, right? The idea of a random forest or bagging or bootstrap aggregation is to generate many bootstrap sample. On each sample, let's fit a tree, and let's just average them. The idea of boosting is to fit many trees sequentially. So I fit one tree, and then another tree, and then another tree, and then another tree. And we don't average, okay, because it's sequential. So after fitting the first tree, I use the results from the first tree to fit the second tree. And after fitting the second tree, I use the results from the second tree to fit the third tree. So I sequentially fit many trees. That's called boosting. And there's an underlying simple philosophy behind it, but I'm not going to discuss it first. Let's first see how boosting actually works, right? What's the idea for boosting? So boosting fits models sequentially. And just like bagging or bootstrap aggregation, boosting is actually a general method. It doesn't have to be used on trees. I'm introducing it in the context trees because trees can be a very good way to construct a boosting algorithm. Just like a tree is a very natural thing to do for random forest. But you can do bagging of any kind of model, okay? Just like I said before. As long as they have high variance and low bias, it's a good thing. Boosting, you can sequentially fit any model. Just for example, you can sequentially fit linear model. Okay, you can fit a linear model, fit a linear model. It just doesn't make so much sense. For trees, it makes a lot of sense. So we discussed that. All right. Now, each model in the boosting is called a learner. just like in random forest, everyone is a learner. We just combine them. So each one in boosting is a learner, and we just sequentially fit a learner. And so here is now boosting can be used for regression and classification. The regression boost is really easy to do. So let me talk about regression first, right? The regression boosting is also called L2 boost or quadratic boost, whatever, right? Because it uses the L2 loss function. The idea is extremely simple. Suppose I have a simple model that's y equal to fx plus e. Okay, that's a regression problem. Now, this f is what I call the base learner. The base learner. All right. What I'm going to do is I'm going to fit this model first. So this is my step one. Step one. All right. Okay. Now, after step one, these are the e's, right? These are the errors I make, meaning these are the things in y that I cannot capture with my fx. So, can I improve it? How can I improve my model? Well, let me try to fit these things, okay? Because these e are the things that I cannot explain in the first stage, right? So in the second stage, my step two, okay? My step two is very simple. I'm going to put the e on this side, and let's fit the fx again. Let's redo it again. I will use my tree or whatever model I'm using to predict the e again. Okay, right? and so what is my final model? My final model. Let me say the final model is G. Okay, G is my final model, or maybe let's use G here, or maybe let's use H here. Okay. All right. So my final model fx. What is it? It's a very simple one. We just add them together. Let's call this H1 because it's step one. This is step two because look, every time you fit, it can be the same H, but every time you fit it, it's going to give you a different coefficient, right? Okay. So actually, let me call this Hx beta 1 because that's let me call this Hx beta 2. So they're the same model, but in the end, you have a different estimate. So my final fx is simply h beta 1 plus h. It's really simple. Okay. It's just very simple. So this is sequential fitting. The idea is very, very, very simple. It's called a sequential fitting. I fit my model first, and then there are some errors I cannot explain. So now let me explain those errors. So I fit the same model to, the model is typically a very flexible model. I fit a very flexible model like a tree to my errors, and then there's still some errors I can explain, and I fit again, and fit again, and fit again. until I'm done. Okay, I'll talk about how to decide when I'm done. But until I'm done, and I'm going to add them all of them together into a final result, and that's called boosting. And it's more powerful than this simple setup may let you think. Okay. Now, in reality, when we do L2 boosting, when we do regression boosting, there's a little bit trick, because it turns out that if you simply do this very simple setup, the model grows too fast. By growing, I mean, these base learners add up together to the final learner, but the base learner adding up too fast. We are fitting the residuals too fast. So it turns out that in reality, it's better to go slowly, meaning grow your final model slowly, so by every time adding a little tiny piece, not add a lot, just add a tiny piece, add a tiny piece, add a tiny piece. Okay, every time, and then every time try to try to slightly and slowly try to fit the residual. Okay, so the empirically that works. Empirically that tends to work the best. So how to do this slowly? Well, the way to do it slowly is when we add them together, instead of saying hx beta plus h, let me just use h1. Okay, h1 is the first step. Instead of h1 plus h2, I have h1 plus lambda h2, and this lambda is the rate of learning, that's what we call it. It's a small number. It could be something like a 001. Okay, that's it. So lambda controls the speed of how we sequentially fit adding things. So once we add a lambda, then this h2 has only a small impact on the final f. All right, and then we can do this for 1,000 times or 10,000 times. You can do the boosting for a long time, because every time you're only adding a tiny little bit to the final model. And of course, in this case, then this mu e, then what we have is really the y, okay? It should be minus the lambda time, the e, okay? All right, let me see. Actually, I think, yeah. So when you see the lambda, then it's really the lambda y minus the h1 from this process, if I'm correct, the residual from the lambda. Okay. Right, so this is total E here, and E has to be minus lambda h1. So every time we minus the lambda, so once we so this E is h2. If we fit this in the second step, but this h2 is only lambda add to the final model, then the third step, so this is step 2. The third step, what is on the left, is E minus lambda times h2, because we're only adding lambda to the model, okay? So then whatever left is E minus lambda h2, and then we're going to fit h3, and then repeat. So that's the regression or L2 boost algorithm. All right. So it turns out that there's another way to understand this whole thing. So one thing is, every time we do some error left, right? I'm going to fit those error. Sequentially, let's do this. Another way to understand is the training data, the data, is continuously being reweighted every time. Now, the bootstrap aggregation method, the bagging method, is we generate many samples, but every sample is the same. All the data points have the same weight in every sample. So we fit them independently, we average them, we aggregate them. In boosting, we are sequentially fit the same model to the same data. Well, you should say that doesn't work. Well, that works because every time we fit, our data is actually reweighted. So yes, you are fitting the same training data, but the training data has been reweighted every time so that the fit is different, and you can add them together. What do we mean by reweighted? The idea of basic idea behind boosting is after I fit each time, okay? After I fit the data, I reweight the data such that the points that are not correctly predicted has a larger weight in the next round, and the points that are correctly predicted has a lower weight in the next round. So in the next round, the data that are previously incorrectly predicted become more important. And I try to fit those data. So every round, I'm trying to fit the data points that are not correctly predicted in the previous round. That is the boosting idea. And then I add all those models together, right? So, so this is the general idea that holds true when we use boosting for regression or when we use boosting for classification, as we'll see very, very shortly. Right? But in the regression case, you can see this is true because every time we are fitting the error term from the previous regression. And what is the error term? The error term essentially indicates how good we predict things. So if on a single data point, if there's one data point where this is the real data and this is my prediction, okay? Prediction. If my prediction is very close, so the error is small, then this data set, this data point in the next round doesn't matter anymore because I make a very good prediction here. And in this case, it means the E is close to 0, so it doesn't matter. In the next round, I will try to fit the large E, right? The large E, okay? Meaning the points that were not correctly predicted or was predicted in the previous round. So boosting is really this idea of every time when I make a prediction, fit a model, these are the errors or these are the points that I'm not making a very good prediction on. Let's make these points more important. Or let's just fit these errors in the next round and then add them together. And then the next round, okay, again, and again, okay? Every time try to correct the mistake made in the previous round. You can think about that way. Okay, and then add them all together. So here is I was thinking about making a drawing, but I suddenly recall that I have a drawing. I have a drawing here that's already made. All right. Okay. So so this is let's assume lambda equal to 1. So when I'm not adding slowly, I'm very fast. All right. So let's fit a tree to this very simple data, right? So y and x has this U-curve relationship. I'm going to fit a tree, and this tree. So this is the first time I fit it. There's a cut here, a cut, right? 1, 2, 3, 3 cuts into 4 regions. So that's a piecewise constant model I have. Okay, so where do I fit very good? Where do I fit not so good? You can see maybe here's not so good, but is negative. But here there's a positive error here. There's a positive error here. There's a lot of positive error here. Now in this region, the errors are relatively much smaller. That's close to 0. So here's it is. Okay, now the blue points here are the errors. Wait, let me see. So it's rescaled. Okay, so it's rescaled. Is it? Hold on. I'm sorry. This picture is just this. So this is the ensemble. But let me say residuals from 3 predictions. Hold on. Right, okay. So this is just this, all right? They're the same, because this is the ensemble. So in the first step, the ensemble, which is the boosting result, is just our H1, okay? Just H1. But I'm going to bring the residuals into the second step. All right, so here we go. Now, these data points are the E from the first step. The residual from the first step, right? Some residuals are negative, okay? So these, in this area, the residual are negative, because these data points, the residuals are negative. And some are positive, okay? So here these are positive residuals in this area. So these are the residuals from the first round, and meaning that these are the data points that we're not fitting very well in the first round. So now let me fit these points, okay? So let me fit another tree. So this is our second tree. This second tree try to fit the residuals from the first round. Whenever in the first round we have some under prediction, like these points is negative in the first round, meaning these points are under-predicted, okay? So, negative means it's over-predicted. My fit is higher than the real data. So now let me add some negative fit, correct? Add some negative fit in the second round. And then add on to the first round model. People understand? Look, so it's like, look, these data points I overfit, right? Overfit, because the real data points are low. So the residuals are low. So in the second round, I'm going to fit a tree that specifically generates a lower, like a fit here. And let me add them to the first tree so that I can fit the points better. Okay? Got it? So we add this tree and this tree together. That gave us the new ensemble that, look, here is much better, right? Because in the first round, it's somewhere here. And now in the second round, we add this point. Okay, we add this thing to the first round so that we're fitting this point much better. So that's the idea of boosting. It's very simple. Okay, however, we sequentially try to fit. Now, of course, you can go on more, right? Here we're still over predicted, so we're still under predicted here. There's still some, right? So we can do a third round, a fourth round, so that gradually our model become very much close to the real data, right? To fit the real data, improving our prediction power. Okay, so that's the basic idea of boosting. Now, classification. If we use boosting for classification, that's more interesting, right? Because classification is not really that straightforward. So before talking about how classification is done, let me just show you the example from classification directly. Okay, let's just directly show the example. Remember, the general idea behind boosting is every time so let's actually go back to the example. In regression, I'm fitting the residual. That's one way to understand. Like I said, the other way to understand boosting is every time I'm reweighting the training data. Reweighting means I make some data more important, make other data not so important. So if you look at the regression case, in this first round, these data points are data points that I'm not predicting very well. They have a negative error. So in the second round, when I say I fit these error, I mean I make these points more important than, for example, these points, because these points are fit very well. The error are close to zero. Okay? So I'm in the second, you can think about the second round as reweighting the data so that these data become more important. These data become less important. So I specialize in fitting these data in the second round. Right? So every time I specialize in fitting some particular data. In classification, it's the same idea. We are reweighting them so that every time I'm trying to fit the mistake I made in the previous round. So let's take a look, right? So suppose this is some data where y is binary, okay, two class, plus and minus, that's the y, where I'm trying to separate the plus from the minus, okay? Separate them, make a prediction, very good prediction. Now, I'm going to consider a very weak learner. By weak learner, base learner. Base learner means every individual model. I'm going to consider extremely simple base model, which is a stump. It's still a tree, but remember a stump is a tree with one split, okay? Simple split, one split. So let's say, this is my first split, okay? So first time I split, I divide, my stump model is I divided it in two parts. Here is the plus, here is the minus. Now, if I do this, then these 3 points are misclassified. Okay, so these are the mistake I'm making in my first round. So in the second round, what I'm going to do is I'm going to make these points extremely important. So here, the size indicates the weight. So I put a larger weight here, I put a smaller weight here. So these points become more important. And then I'm going to fit a stump on this weighted data, where these points are most important ones. Okay? So that's my second step. These are more important, so now I'm trying to fit these really well. But then also, I make these three, I make this cut. So again, these 3 become my mistake. So let's make them really important. Okay? And I'm going to make another cut that guarantees that these 3 data points are correctly specified. But then 1, 2, 3, these 3 data points become misclassified. Let's make them important again. And you can do this forever, right? But let's just do 3 rounds. Just do 3 rounds. And just do these 3 rounds, and then let's add all the cuts together. Okay, let's add all the models together to make a final model. What is our final model? Our final model is these 3 cuts, and we have a perfect classification, right? Okay, so that's up, right? So after 3 rounds, we have correctly classified all data. This is by this reweighting, and continuous fitting procedure. So this is a very good demonstration. And then, of course, so I combine them with, so this model has a 0.4 weight, this model has a 0.6, this 0.59. If you add them all together, then we have the final model. This final model is a perfect classification of all the data. That's boosting for classification purposes. All right. Now, can you do this with a single tree? Right? Can you just use a tree and just cut it 3 times and make a perfect one? You may, but again, boosting turned out to, in many cases, boosting turned out to be a better idea, because the one thing I haven't mentioned is, in order for boosting to be really successful, the base learner, which is each model you fit, you want to make it simpler. Okay, you don't want to have a very complicated. So you don't want to have a very large tree for each base learner. You want it to have something like a stump, a simple model, but then you learn very, very slowly, so that every time you focus on using a simple model to classify a few important data points, and then you move on to other important data points. Every time you use simple model to separate them or to fit them, and then you get everything together, you get a very complicated model that typically performs very well. That's the idea of boosting. Okay. All right. So again, like I said, behind the classification boosting, we have some algorithm. But before talking about where this algorithm comes from, I am going to say, in essence, what boosting is. Now, boosting sounds like an interesting idea, but there is a unifying underlying philosophy that ties boosting with extremely large class of models that we either have studied or will study, or will not have time to study, but it's out there, right? Boosting, in essence, is what we call a forward stage-wise algorithm. It's also the adaptive model. Okay? It's an adaptive algorithm, just like a tree. It's itself is an adaptive algorithm. It's called a forward stage-wise. What do we mean by forward stage-wise? Here's the idea. Actually, let me go back to my to regression. Yeah, why not? Okay. Aha. Yeah, there we go. Okay. Oh no, not this one. There we go. Okay. All right. Remember this basis function and linear basis function model, right? So when we talk about regression, I said that a piecewise constant model. This is, we can think about the piecewise constant model as something like this, where each one is a function, so each phi, in piecewise constant model, this phi is whether x belongs to a certain region, right? Okay, so if this phi is whether x belongs to a certain region, if that's function, then I can just put it here, so it's beta 1 times whether x belongs to region 1, plus beta 2 times x belongs to region 2, etc., etc. That's a piecewise constant model. But this phi can be anything, right? It can be any function. So if this phi is any function, what do we call it? We call this phi, we call it basis function. And if we add them linearly together, that's called a linear basis function, right? Okay, so we talk about this in the very beginning, and we say linear for linear basis function, you can actually do OLS, because you can combine all the phi into a large matrix, and you can just do. Right? That's the analytical solution or less solution, because it's a linear model in the end. Right? It's just that for the linear model we don't have x, we have phi x. So one way to understand the linear basis function model is that it is a linear model, but we do a feature transform first. What do I mean by feature transform? I transform x into phi x, or into z. Let z be phi x, right? So I transform x into a z space, and then I have a linear model on z, right? So that's the. If we remember the picture, where's the picture? Yeah, feature transform, right? Okay, so x may look like this, and then I can transform x into sine x, and then immediately we have a linear relation, right? Kind of model. That's a feature transform. So linear basis function model turned out to be extremely general. Right? Many things are essentially linear piecewise linear function basis function models. What is a linear basis function model? A tree, right? Because a tree is a piecewise constant, and a piecewise constant is a linear basis function model, with the basis function being whether x belongs to a certain region. Okay, so a tree is a piecewise constant. A piecewise constant is a linear basis function model, and right, with each basis function being whether x belong to a region. What else is a linear basis function model? A random forest is a linear basis function model. Why? In random forest, we have generating many bootstrap samples, and we're combining them together. So in random forest, we're combining many trees. So let each phi x be a tree. Can I? Of course. A tree is a function of x. The tree itself is a function of x. So let this be a tree. And then what is random forest? Random forest is combining these trees together, right? So what is the beta in random forest? If we have n trees, if we generate n trees, then this beta is 1 over n. Because each tree is given the same weight. Because we're averaging them, right? Especially when we do regression trees, right? Regression random forest. When we do classification, there's a sort of different, like the majority works out, right? But when we do regression, each beta is just 1 over n, the number of trees, and we're averaging them. So a random forest is a linear basis function model. Now, of course, what is boosting? The boosting is a linear basis function model because we are adding trees together. Okay? Well, let's fit one tree first, let's fit the second tree, the third tree, and then we're just combining them. Right? Okay? And okay, so that's the first point. The second point is the difference between boosting and so boosting is function in terms of functional form. Boosting and the random forest are both linear basis function models, but in terms of execution, what I mean by execution, in terms of estimation, they're quite different. In boost, how do we estimate a linear basis function model? Now, suppose I know this is my model, right? Then what I can do is I can suppose I know phi. Suppose phi is just phi x is just it's just x, okay, or whether x belongs to. Suppose phi x is just x. So if beta 1x plus beta 2x2 plus beta 3x, and then I can always do the OLS solution, and that's it. We're done. Now, but what if each phi is a tree? Then that thing gets more complicated because why? Because tree doesn't have a fixed functional form, right? Because tree itself is adaptive. Remember? So the functional form of tree is a piecewise constant, but what is the region depends on the data. So in other words, the tree doesn't have a fixed functional form. It completely depends on what the data looks like. So in this way, you cannot do this, right? Because you do not really know what this looks like. So how do we find out the optimal value for beta when we are combining trees? Now, if you want to estimate a model where each basis function is a tree, then theoretically, you need to find out the optimal value for each tree. You want to fit each tree, and you want to find out the optimal value for beta. So you want to find out what is the optimal beta, what is the optimal tree, what is the optimal beta, what is the optimal tree. You need to think about this as the optimization problem. The optimization problem is a huge problem, right? Because you want to fit each tree and fit each beta. So that can be extremely hard to do optimization problem. Sometimes when your tree is, we have a lot of trees, we have like 10,000 trees, 5,000 trees, it's almost impossible to do, right? So there are two ways to do it. The first way is forget about optimizing beta. I'm just going to let each beta be the same. I'm not going to figure out the optimal beta, okay? I'm just going to simply adding them all together and divided by, like average them, okay? Which is a random forest, right? So random forest, forget about fitting the beta. It's just fitting the trees, and that's it. So that's a simple way to do it. It may not be the best, right? Because you can think about one thing you can think about is if you are doing random forest, why do we have beta equal each other? In random forest, every beta is the same, which is 1 over n. But is it the optimal beta? Do we have to have 1 over n? Maybe we can change the beta to have a better result, right? But we don't do that because we don't know how to do it. The optimization is too hard. Right? Okay, boosting is another way. Boosting try to fit the beta. Okay, boosting try to give a different weight to each different model. But the way it does it is step by step by step. So let's fit this one first. Forget about this, okay? Let's fit y equal to beta 1, phi 1 first. So our first round, in round 1, let's just do y equal to beta 1, phi 1x. Let's find out the optimal phi, and let's find out what the beta 1 is. So that's the first step. The second step is, okay, y equal to beta 1, phi 1x plus beta 2, phi 2x. Now, in the second round, this thing is already fixed. It's like a constant because it's already produced by the first stage. So in the second stage, I only focus on fitting this one to this one. Okay? This one doesn't change. It comes from the first stage. And of course, in the third stage, I take these two as given, and I try to fit beta 3, phi 3. Okay? In the third stage, I take these two as given. That's called a forward stage-wise regression, meaning we go stage by stage by stage, and we go forward, forward, forward until some stopping point. Now, is it the optimal way to do things? Is it the optimal way? It's not. Why is it not the optimal way? Because ideally, if I'm going to fit this model, right, I should try to find the optimal beta 1, phi 1, beta 2, phi 2 together. That's the optimal solution. I should not take these given because here the way to do it is the value of these things are coming from the first stage, which is a simpler model. But of course, using this model to produce the beta 1 and phi 1 is not the optimal beta 1, phi 1 in this model, right? Okay, remember? Once you add something, the optimal value here changes as well, because they are correlated. Okay, right? So if you think about fitting a linear regression, if you say okay y equal to beta 1x1, that's your first stage. You get a beta 1, and then you fit y equal to beta 1x1 plus beta 2x2. But you take the beta 1 value from this model, then is it going to be the best beta 1 value? No. It's going to be different than you try to fit beta 1, beta 2 together. That's the optimal, right? So for boosting, we take this value from the first stage. We do not fit this together with this because we want it to get simpler. We want our optimization problem to be simpler. We don't want to fit everything together. That's too hard. So this is called stage-wise. But stage-wise, is it the optimal way to do things? That's not the optimal way because the optimal way we don't know how to do. The optimization problem is too hard. So we do this stage by stage by stage. And that's essentially the spirit of boosting. Okay? So every time we take the previous stage as given and then focus on this new problem, and then we take these two given and focus on this new problem. So boosting is essentially this forward stage-wise algorithm. But in essence, it's a linear basis function model. It's a linear basis function model, but we try to do stage by stage by stage in a forward manner in order to search for an optimal solution. All right. You can also say boosting is an adaptive linear basis function model, meaning the linear basis function model has this n terms, right? And every phi is a basis function. So in boosting, every phi, the basis function is an adaptive function, which is a tree. So every phi is a tree, which is adaptive, and the whole model is adaptive, meaning the m is now fixed. The m depends on the data. Okay, so where do we stop depends on the data. I'll talk about how do we stop, but in essence, how do we stop depends on where the data is. Okay, what the data looks like. So the whole thing is all adaptive, right? And then it's a forward stage-wise. Now, one thing before talking about the detail of forward stage, like how boosting does the forward stage-wise, I just want to again make you recall the other kind of forward, stage-wise thing that we have learned. If you remember, what kind of model have we discussed? That's called forward something. Do you remember? In model selection, what have we talked about? Do you remember this? Right? Forward stepwise regression. Okay, I call it forward stepwise selection. It's it's typically also called forward stepwise regression. So do people remember what forward stepwise regression look like? Like the algorithm. The idea is I have a y and I have a bunch of x. I don't know, right? So my candidate x1, x3. I don't know which one is important to me. So let me try find one of them first. Say x2. So let's estimate beta 1 x beta 0 x2 first. Okay, and then I pick the next one. So I go from beta 0 x2 to beta x0 plus 2 plus beta 1. And then I choose one of them. Maybe the next one is 1. So I pick beta 1 x1. And then and then I can go, right? So maybe I stop, maybe I do not stop. This algorithm is called forward stepwise. It's not called forward stagewise. The difference between stepwise and stagewise is that for stepwise, every time I add something new, I also go step by step. But every time I add something new, I estimate the beta together. So here the beta 1 and beta 0, beta 1 are optimal given this model. Okay, estimate together. Stagewise means I take this beta 0 from the first step, from its first stage. Okay, so when I do so that's why one is called stepwise, the other called stagewise. The other link I want to talk, the other thing I have mentioned, when I talk about forward stepwise selection, I said why do we need to do forward stepwise? Remember, I can always do if I have these 4 models, right? So I want to select which one model is the best. Then why do I even do forward stepwise? I can just compute all 4 models and look at which model performed the best out of sample. Okay, calculate a validation error or do AICBC. I can just see which one model performed the best. I pick that model. Why do I do forward stepwise? Do people remember? When I described this, I said something along the lines of why we need to do forward stepwise. Why I cannot just compute all the models and see which one's the best. The reason is, when we only have 2x, x is 2-dimensional, I have 4 models. If x is 50-dimensional, how many models do I have? 2 to the 50. All right? I don't even know how many digits there are, right? 2 to the 50 models, if you want to compute all of them, it takes a huge amount of time. And so optimization is too hard. So when optimization is too hard, meaning you cannot simultaneously compute all the models, select best one, we do the forward stepwise algorithm. The forward stepwise algorithm is not guaranteed. It's not guaranteed to find the best model because it's only an approximate method. It doesn't guarantee you to pick the best out there, but it saves a huge amount of computing time. Okay, so the forward stepwise algorithm is a computationally efficient way to find out the approximate best solution. Right? It's like, it's like any optimization. So you can think about the forward stepwise algorithm as not as a model, more like a what? More like an optimization algorithm. What is the optimization algorithm? Well, suppose this is the beta star that really maximizes all the things, everything, right? So you want to start with any beta 0, that your initial guess. And you want to use an algorithm to guide you toward this optimal point, okay, to reach this optimal beta star. So numerical optimization algorithm exactly does this purpose. All right. So for example, suppose this is what your loss function looks like as a function of beta. Here's where you'll start. You want your algorithm to find a way to guide you, point you toward this optimal point. Right? Okay. So maybe you take a derivative and go along this direction, right? So this is, so this is one way to get there. Forward stepwise algorithm is one way to get to the optimal solution, but it's not guaranteed because it's an approximate solution. It's computationally efficient, so you don't have to compute all the different models to find out, right? You just need to stepwise, step, and try to approach, but it doesn't guarantee. So oftentimes you can reach some place that's not the optimal, but it's computationally efficient. Okay. Now it turns out that this is the spirit behind forward stepwise or stage-wise algorithm. Let's take a look at boosting our regression again. Where is it? if I have a linear basis function model, and suppose the potential M is huge, okay? So if a huge, I can fit in a large number of trees. I want to optimize, I want to find the optimal value for beta and the phi together. It's impossible optimization task. So how do I try to find a best solution to a computationally impossible task? I do step by step by step. So that's boosting, okay? So the forward stage-wise algorithm, just like forward stepwise, is a computationally efficient way to try to find the solution to this joint problem of estimating beta and phi in a linear basis function model. Right, so that's the spirit behind boosting, okay? And then that's the spirit behind all kinds of forward stepwise or stage-wise algorithm that you will find. Right. Okay, so with all those philosophical things behind, let's take a look at the actual boosting algorithm, right? Where is it? Okay. All right. So yeah. So now let's take a look at how boosting is actually done from the perspective of a linear basis function model. Okay. So this is our linear basis function model, and I want to find the optimal value for phi. Now let me just suppose that beta is a parameter for phi. So I want to find the optimal value for beta, and let's suppose the weights are alpha. So I want to find the optimal value for alpha. So I want to solve for the best value of alpha beta together of this model. And I don't want to optimize them all together because that's too hard. So I'm going to do step by step. So the first step I do is I define a loss function. Okay, I need to define a loss function of y from x, right? Because this is my f and there's a y. So I define a loss function. And then once I define a loss function, I'm going to do this step by step. So in the first step, I'm going to only fit y as a function. My f is only going to be the first term, right? Alpha 1, phi 1. And then once I fit that, my second step is taking this f as given. So this f is from my first stage. I take it here, I put it here as if it's already fixed. And then I add the second term. And so the second stage, what I'm doing is I'm fitting this model. Okay? So this is the loss function. So I'm minimizing the loss function of y with respect to this new model. But this new model is f from the first stage plus a new term. And this new term has two parameters, alpha 2 and a beta 2. So the second stage is try to find the best alpha 2 and the best beta 2. Right? So people, I hope that's clear. That's basically what I just described, right? Okay, so the first stage is try to find alpha 1, phi, beta 1. The second stage is take these as given, that already fit it. I try to find out alpha 2, phi, x, beta 2. I try to find out these two values by minimizing the loss function. So if we are doing regression, then the loss function is y minus this whole thing squared. Take this as given, right? Take this as given from first stage, and only fit the second stage. Okay, what is this taken as given? Like what is this? What is this thing? If this is already given from the first stage, that's just the residual from the first stage, right? So in essence, what I'm doing is in the second stage, what I'm doing, I'm fitting the tree to the residual. Okay, so that's the regression, right? That's the L2 boosting. Okay, all right. Now for classification, it's a little bit more complicated. There are different ways of doing classification boosting. The most popular way to do classification is called gradient boosting, which I'm not going to talk about. Okay, I'm going to talk about another method which is specialized in doing binary classification. So y is equal to 0, 1. So when y is equal to 0, 1, then it turns out that to do classification in that case, using a popular boosting algorithm, it's a little bit older, but it's called ADA boost. So using the ADA boost algorithm, we are minimizing we actually minimize a special loss function. Now, remember, when it comes to classification, we can use a bunch of different loss functions. So one loss function is the 0, 1 loss function. Okay? If it's correctly classified, it's 0. Incorrectly, it's 1. But the 0, 1 loss function, I already said last time before that it's very hard to optimize. Okay, very hard to differentiate. So it's typically not a good choice. So we need to find some other loss function that's good for classification. One loss function we have already talked about is the logistic loss function, right? The logistic regression loss function, which is the logistic cross entropy loss function, right? So we have here, okay? So this is the binomial cross entropy loss, which is the logistic regression what it uses, and the binomial one look like this, which is similar to the misclassification, right? To misclassification or the 0-1 loss function, in the sense that it penalizes incorrect, but does not penalize correct. So if we're using AdaBoost for classification, we are actually using this loss function, this new loss function that you probably have never seen before, but it's called exponential loss because it's easier to do. And the exponential loss is defined as the exponential of minus y times fx. So here the y is a binary, 0, 1. So what is y times fx? I think I also talked about this before. You may have already forgot. But when I talk about classification, there's a concept I introduced called the margin. Do people remember? So margin means y times f, okay? So y times f is margin. Now, what does it mean? If y is, so here y is not 0, 1. I have to correct myself. When we do this, y is plus 1 minus 1. So f is a function that if it's plus, it's positive, we predict y to be plus 1. If f is negative, we predict y to be negative 1. Which means if y times f is positive, that has to be either y is positive and f is positive, or y is negative and f is negative, which means they're correctly classified. So whenever the margin is positive, it's correct classification. Whenever the margin is negative, it's negative classification. It's an incorrect classification, right? Okay. So here in this picture, we are plotting the loss function as a function of margin, right? So when margin is positive, the 0, 1 loss function will have 0. And the 0, 1 loss function is 1 here, okay? And the binomial cross entropy, which is the loss function used by logistic regression, look like this. And exponential loss actually look like this, which is an exponential function. But they're all very similar. So we can use any one of them. The idea is we want to penalize negative margin and reward or do not penalize positive margin, because positive margin means your classification is correct. Again, when I discuss why we do not use linear regression for classification, it's because linear regression, when we say linear regression, right, linear regression has a different meaning, but when we say linear regression, we mean the use of L2 loss function for OLS use L2. When you use L2, that's really bad because the loss function look like here, which means the positive margin are also penalized. Right? You penalize correct classification. That's bad. Okay. So here we're using exponential. Now, it turns out that if we use exponential loss function in AdaBoost, then we can solve. Where is the solution? The solution is here. Okay, let's click it. Oh no. So the slides is malfunctioning. I need to correct it, but here it is. Okay. So if y is plus 1 minus 1, then it turns out that in every stage, you take the f from the previous stage and plus the alpha times phi. And what you're doing, you're minimizing this loss function. This loss function is the exponential loss function. So exponential times the negative margin. So this margin is y times our model. But what is our model? Our model is the f from previous round plus the new things I'm adding. The new things is alpha times this basis, like this tree or something, right? This phi, okay? So the phi is a tree or something, or a model. So what I'm doing is I'm trying to optimize alpha and the phi together in the second round, or in this new round. Now, of course, this is already from the previous round. Okay, so I can take the y and the f from previous round, and together I'm just going to call it w. I'm just going to call w. Okay, so what is left is the exponential of negative alpha times yi times this phi. That's what I'm really optimizing. So you just take a derivative. So if I want to know the optimal alpha, I just take a derivative with respect to alpha. If I want to know the optimal phi, I just take derivative with respect to phi. And the solution is here. Okay. Solution, the optimal alpha has this formation, has this solution, which look like this, all right? So, I'm not going to go detail. You can look at it. And the optimal phi has, now the optimal phi has this form, okay? Which is what? Which is the solution to this problem. So the optimal phi is the solution to this problem. But what is this problem? This problem is the weight times whether my phi is the same as y. So now let's think about what this phi is. This phi could be a tree. If this phi a tree, then phi x is the prediction of the tree. So whether y equal to the prediction of tree, what is that? That is simply the 0, 1 loss function, right? Okay, right? So this is whether the tree prediction equal to true y. what is the, let's forget about this W, okay? What is the thing that minimizes whether my prediction equal to Y? Well, that is just fitting the tree itself. When you fit the tree, you are minimizing. You can think about you are minimizing this misclassification rate. Okay. Of course, when you actually fit the tree, you don't use the misclassification rate to guide you. But you know the essence a tree minimize. If we do not consider this weight, then the tree minimize the misclassification rate, which is the optimal tree here. But the difference here is we are actually minimizing not the misclassification rate. We're minimizing the weighted misclassification rate. This weight is the W from what? From here. This W is Y times the F from the previous round. So this W is the weight. So in other words, when I try to find the best tree in the second round or in the nth round, the best tree is not the tree that minimizes the misclassification rate on the original data. It is the tree that minimizes the misclassification rate on the weighted data. The weighted data is every point has different weight, have a different W. And where does this W come from? This W comes from the previous round. So in the previous round, if the data does not fit very well, the W will increase. If the previous round, if the weight is the data is fit well, the W will decrease. So so my tree, my task in this round is to find a tree that fit this weighted data best. And that's the idea behind classification rate. Okay, but the detailed formula is here, right? Okay, where's the detailed formula? Here's the detailed formula. Okay, all right. Here's the this is just from the solution that we just saw, the solution to the stage-wise algorithm, right? So every time I fit a tree to minimize this weighted error, okay, and then after I fit this tree, I'm going to update my model. When I update, I let this W, I update W. The update W depends on how well I fit this time. And finally, when we add tree together, we add the tree according to this alpha, but this alpha is really equal to this thing, okay? So this alpha is equal to log 1 minus error divided by error. This alpha is also the optimal alpha. I'm going to combine my trees, which is also from the the optimization process I just talked about. One thing interesting about this classification tree is that this alpha can be either so this thing, okay, let's think of the epsilon is the error I make in each round, in the previous round, in each round. But this epsilon, think about this epsilon. This epsilon can be, you can think about this epsilon as the weighted misclassification rate. But the misclassification rate is between 0 and 1. So if this epsilon is larger than 0.5, it means I'm misspecifying a lot. If this epsilon is very low, it means my model is largely correct. So if epsilon is small, less than 0.5, what is this? If epsilon less than 0.5, this whole thing is larger than 1. Take the log, alpha is larger than 0. But if epsilon is larger than 0.5, this alpha is negative, meaning that my model is negatively added to the final model. Okay, my tree is negatively added. Why? If epsilon is larger than 0.5, my tree is negatively added to the final model. How is that possible? I'm actually a minus tree, I'm not adding a tree. Why is that? So one thing we should remember here is that I've assumed y. So one trick is y is actually minus 1. This is binary classification. So y is either minus 1 plus 1. So in this case, if my model, if my tree has an epsilon larger than 0.5, that means e larger than 0.5. That means the tree misclassifies more than it correctly classifies, right? So most of the time it's wrong. But y is minus 1 plus 1. So which means if I negative tree, if I just negative it, then I'm going to be mostly correct, right? Okay? So that's why, all right? So if a tree is mostly correct, we let it positive. If a tree mostly wrong, we flip it, become negative, and then it's mostly correct. So then we add it. So if we're adding a negative tree, we're adding something that's positive contribution. All right? Okay. So this goes back to the idea that when I talk about the wisdom crowds. I said the wisdom crowds is you combine many individuals and you can get a better prediction. However, with one caveat, which is if each individual has a better than 50% probability of being correct, meaning everybody is good, doesn't have to be very good, it can be weakly good. Then you combine them, you get a very strong prediction. But if everybody's below 0.5 correction rate, and you combine them, you get a very bad one, right? So here's the same idea. If each individual learner, like a tree, individual learner is weakly good, has error below 0.5, then you add them, you just throw them into the model. It's going to improve things. But if it's weakly bad, even if it's bad in the sense that its error is larger than 0.5, you should not add them because it weakens your prediction, right? But you can flip them, okay? Once you flip it, it's still good, and you just add them in together. Right. Okay, so I'm now going to go into more detail about this. I'm also running out of time, but before we go, right, let's, because I thought I could have finished the whole thing today, but I'm taking too much time. All right, so let's take a look at a very simple simulation first, before looking at some real data analysis. The real data analysis has to be let's wait for Thursday to do the real data analysis, but let's do some simulation. So I'm going to generate some data for two-dimensional classification problem. So the underlying P is so Y is a Bernoulli 0, 1, and the underlying P has this expression. Okay, all right. So that's so that gives us a 0, 1. That gives us a 0, 1 kind of boundary. So the true boundary. Okay. So this is what. Now, if you look at this, because I'm running out of time, I'm going to speak fast. But according to this model, the true decision boundary is x1 plus x2 equal to 0. Okay? So this is the true decision boundary that separates the two classes. And this is what the data look like. All right, x1, x2, the true decision boundary is here. Okay, there's still going to be some overlap because of the probability. But the biggest decision boundary is this x1 plus x2 equal to 0. All right, I wanna separate them. So the first thing to do is run a logistic regression. We can use a logistic regression try to separate y equal to 1 from y equal to 0, and my logistic regression performance is very good. Why? Because the original data is because the data is actually generated from a logistic regression model. Okay, so it's basically a logistic regression model, right? It's a Bernoulli function with a p equal to do you recognize this logistic model? I hope. Y is 0, 1, based on the probability, but the probability is this is a sigmoid. People remember? Okay. E plus this is sigmoid, right? But this is just equal to minus x, all right? Okay, so this is a sigmoid. So this is the logistic regression, and I should use the logistic regression to find the perfect separating boundary, right? Okay, so my logistic regression is very good because it's the true model here. Now let me try to use. So this is the test data. So I have training data, I have test data. Let's bring the data onto the test data, and our misclassification rate. So this is true y. This is the y hat. And so these are these are correct classification. These are incorrect classification. So the classification rate, misclassification rate is 0.70. Okay, 70% misclassification rate. All right. Let's do a tree. Okay. So we fit a tree using our power function. We first grow a large tree, and then we prune it. Okay, so prune it back, and our final error is 0.22. Not too bad. Right? Not too bad. It looks something like this. Okay, right. So we'll make a separate cut. The tree looks like it. So like I said before, a tree can capture nonlinear relationship, but it's actually pretty bad with linear relationship. So right in this case, our relationship is actually linear, but tree has a difficulty capturing that. All right. Okay, so I give you this relationship. All right. Let's do bagging. Now, if you want to do bagging in R, you actually use the random forest package. So I use the random forest. Now, in random forest, you have to specify a parameter called mtry. The mtry, remember the idea of random forest is that in every split, I randomly select a subset of the variables to split. I do not consider all the variables. So the mtry is the number of variables you want to consider every time you do a split. Here, what if you do bagging? Bagging means every time you consider all the variables. So when you do this function, you simply say, okay, suppose you have 10 variables. then you just say m try equal to 10. That means you're doing bagging. If you say m try equal to 5, that means every time out of 10 variables, I'm randomly select 5 variables to split, to consider for splitting. Okay? So m try essentially tells you whether you're doing bagging or random forest and how many variables you're considering every time. So here we only have 2 variables. And of course I'm not doing random, I'm just doing bagging, so m try equal to 2. Okay? And so we do the function, and then here's the result. What does it look like to you? Here's the decision boundary, okay? What does it look like to you? Right. One thing you should know, that it looks like overfitting, okay? It's severely overfit. The boundary is too complex. Actually, you can see the reason why it does this is, look, here's some data that is plus. Okay? These are triangle. So there's some plus here, that's why it generates a little bubble here, right? There are some triangle here, that's why it generates some bubble here. So it tries really hard to fit every data point. And that's overfit because the true boundary is like this. So even at the true boundary, you are going to have plus here and triangle here. Why? Because it's the underlying probability model. So there's some E that is not explained by our X. It's very simple. But now it's picking up the E. So it's overfitting, right? So how do I do it? It's very simple. I'm going to say, okay, so let me, now in reality, I'm talking about how do you do this in reality, but a trick is you can simply set a limit to the number of nodes in the tree, right? So you can say, okay, I can say max nodes equal to 8, meaning I want the tree to be smaller, like only 8, okay, only 8. So this is random forest. Random forest means combine many trees, but I want each tree to have a limited, very small depth, not too large. Right? So in that case, I can limit the complexity of each tree, and then I combine them. Okay, so in random forest, and by doing that, I can produce this much smoother boundary. Okay, much smoother boundary. And that looks okay. It's not very overfit. Right. All right. And the error is 20%. Okay, so we go from 22 to 20%. Remember, the best case, the logistic regression has 17, I think. So right now it's 20%. Right? It's pretty close to logistic regression. In reality, this max nodes or the tree depth for each random forest, you can tune it. By tuning, meaning you can try different values for the depth of each tree, and then you can see how good it performs on the validation data set, and then you pick the one that generates the smallest error on the validation data set. It's the same idea of regularization, or the same idea of model selection, right? Using a validation data set or using cross-validation to find out the best value for the depth of each tree. Okay? You can always use cross-validation to do all this kind of tuning process. All right. To avoid overfitting, right? So now let's do boosting, right? So for boosting, we use a package called GBM, and for this function, what we do is, first of all, we are using ADA boost because ADA boost is the algorithm for classification, and then the number of trees. So boosting, you have to separate. Okay, how many rounds? Okay, how many iterations do I do? I do 5,000 iterations. Interaction depth meaning. For in each iteration, what is the depth of the tree? Okay, how large a tree I fit in each iteration? Let's say 10. Okay, depth equal to 10. Shrinkage one that doesn't matter. Okay, so we don't have to. So shrinkage factor really means how you add the tree together. Okay, so do you add it slowly? Do you add it fast? So here's the result. Okay, so again, it's overfitting. So whenever you use this adaptive method, if you do not tune it, if you do not choose the optimal parameter, then it's very likely to be overfitting, right? So let's tone it down a little bit. Let me fit a tree with 4,000, not 5,000. Let me limit the depth of each tree to 2, not 10. Okay? And let me add the trees slowly, shrinkage slowly. And in that case, again, I give you a much smoother boundary as a boosting, and I achieve a error rate of 19%. Okay, so still worse than logistic, because logistic regression in this case actually perform the best. Right? Now, again, in reality, when you do this, when you do boosting, you have to tune these things. Okay, so you have to use cross validation to find out the best value for this these are so-called what? These are called hyperparameters, right? Remember from regularization, these are called hyperparameters. So you need to use cross-validation or a validation set to choose the optimal value for them. Again, finding the minimum point on the U curve, okay? Right? Because otherwise it's very easy to overfit. You're going to have very complicated models. Okay, so that's our simulation 1. Let's take a look at simulation 2. Now in simulation 1, we try to use tree-based methods to capture linear decision boundary. And like I said, the linear decision boundary is very hard to capture because trees do not capture simple linear relationship very well. So we can use boosting, you can use bagging. None of them give you the true decision boundary, which is linear. So so these methods struggle to capture the true linear relationship, right? Okay. So what do? Well, in simulation 2, I'm going to have a binary classification problem with a non-linear decision boundary, right? So here's the data. We have 2 classes. One class is here, the other class is here. Now the decision boundary is completely non-linear. There's no linear line that can separate them, okay? Right? So let's try, okay? So in that case, let's try the different method. Again, I'm going to try the logistic regression first. Let's try the linear logistic regression, and it doesn't, the linear regression were completely unable to do this problem, because the problem is there's no linear boundary can separate them. Okay, so if you look at the prediction, the logistic regression predicts everyone to be 1, to be the first class. It's completely unable to predict the second class. Okay, because why? Because the logistic regression essentially for this column, it probably give you a line like here, and then which says, okay, all of this is black, all of this is black. It predicts black for everybody. It's impossible to predict blue. So logistic regression completely fails in this case, right? Well, I shouldn't say logistic regression completely fails. I should say linear logistic regression, because logistic regression can do nonlinear model too. You can say y is a function of x, but you can say y is a function of x plus x squared. Okay? In that case, you can actually generate nonlinear boundaries, which perform pretty well. But anyway, so here I'm already doing this, right? So sorry, I'll speak too fast, but when we do logistic regression, we can do a polynomial model x1 and a polynomial x2. So you can have x1 squared plus x2 squared. And we do logistic regression. So in this case, it's a nonlinear logistic, quadratic, and we can generate a boundary like this. So even logistic regression is not always linear. You add some nonlinear term, then it's a nonlinear boundary. The classification rate is 12.67, okay? 13%. Is it good? I don't know, but it looks pretty good, right? By the way, when I say misclassification rate, this is on the test data. This is not on the training data, okay? On the test data, 13%. How about classification tree? Let's do a tree. Well, the tree will give you something like this, right? Because the tree is piecewise constant. Is it good? It's not as good as logistic, because the error is now 14%. So the error becomes higher. So again, a tree gives you a very nice interpretation. Like, it has a tree structure. It's very nice. It captures nonlinear, etc., but oftentimes it's not the best prediction machine. Okay, the error is high now. But now let's try random forest. Okay, so bagging. So if I do bagging, then I just do this. These parameters are chosen after tuning. So for bagging, I produce an error of 12.33, which compared to the logistic regression is slightly, but they're same. Okay, basically same for bagging. All right. What about random forest? So when we go from bagging to random forest, because we only have 1x, 2x, by random forest I mean every time I only try one dimension in split. Okay, I do not consider both. So I make the trees more independent of each other, and after that, the error comes down to 10%. So now we're doing better than logistic regression, right? Okay. And produce something that still looks a little bit overfit, but that's the best I can do. Right? So that's a random forest. And finally, we do boosting, where we do. So here actually I'm showing you how to tune it, because I'm using the train function from a package of caret that automatically will help you do cross validation to find out the best value. So here I want this function to try 500 trees, 1,000 trees, 5,000 trees, and I wanted to try interaction, meaning the depth of each tree from 1 to 10. I wanted to try all of them, and the shrinkage either 0.01 or 0.01. So I want the function to automatically try all the different combinations of these things and use causal validation to find out the optimal point, okay? So this is from the train, this is the result that shows you different hyperparameter. So this is when shrinkage equal to 0.1, 0.1, and then this is number of trees, okay? And this is the max tree depth. So 3 variables. You can pick the one that gives you the smallest, okay? So we're going to pick the one that has the smallest, so this is accuracy. So we want to find the one with the largest accuracy. Somewhere maybe here, or maybe here, that has the highest accuracy. We choose that combination. And this is the result, okay? So this is our final result. We pick 500 trees. Each tree is limited to a depth of 4 with a shrinkage of 0.01. So this is after using cross validation to fine-tune the model, okay, to choose the best hyperparameter. And the test error is 0.12, okay? So in this case, and this is our classification boundary. So what is the moral over here? Right? We see 2 examples: linear and nonlinear boundary. Now in the first example, logistic regression by far is the best because that's what it is. In the second example, logistic regression is still pretty good for nonlinear. Okay, for nonlinear model, still pretty good once you add the polynomial terms into it. But random forest can a little bit, beat the logistic regression by about 2% misclassification rate. You can bring down to 10. But boosting is not really very good. Bagging still doesn't really beat the logistic, right? And the tree is very bad. So at least in these 2 simulations, we probably haven't really seen the full power of how random forest. And in the next example, next class, I'm going to show you this new Polish bankruptcy some data where it's real data. We'll try to forecast bankruptcy rate. For this problem, logistic regression is nowhere near the performance of tree-based math methods. Why? Because, let me just one final line, which is this. The reason why we are going to pick a logistic regression model that performs really well on this data set, the reason why we're able to do that is because we have only 2 variables. So we can let one variable go to square, the other variable go to square, and we have to look at the data first. Right? So we are already using the eye to pick the model. So when you have a lot of variables, how do you decide a polynomial model for logistic regression? It's impossible. Okay? And in that case, even if theoretically you can use logistic regression to do once you pick the correct polynomial model, in fact you're not able to do so. And the random forest and the boosting can give you much better results when we're dealing with real data. Okay? All right. So sorry for too long today, and we're going to continue on Thursday.